Hello everyone. Today what I wanted to talk to you about is give you an overview of gravity and projectile motion. Most importantly, I wanted to talk about what gravity is and what gravity is not, and also give you some insight into how to solve projectile motion problems. Gravity is a force of attraction between two objects. Down here you can see a baseball, and there is a force due to gravity acting on it downward. I've also labeled the air resistance here, but in most cases we're going to sit there and ignore it. We're going to sit there and treat objects that are under the influence of gravity much like if they were just falling on the moon. Just the force of gravity acting on them. Gravity is not an acceleration. We do say that there is an acceleration due to gravity, but that does not make gravity an acceleration. Gravity is also not a velocity either. The acceleration due to gravity is constant near the surface of the Earth, or at least we treat it that way for right now. The rate of acceleration close to the surface of the Earth is 9.8 meters per second squared. As long as we're ignoring air resistance, all objects do fall with the same rate of acceleration, but this means that if two objects that are close to the surface of the Earth and they have very different masses, they will experience very different forces of gravity. As you can see in this example of an elephant and an ant, we have accelerations of 10 meters per second for both of these objects. The accelerations are constant. That is to say that both of these objects will fall at the same rate. And what I mean by rate is they will fall at the same acceleration rate of 10 meters per second. But in order to do that, our elephant here has to experience a very, very large force due to gravity, while our little ant over here has a relatively small force acting on him. So with this, the ratio of the force to the mass of the object is what gives us the acceleration. And in this case, both the elephant and the ant will fall with the same acceleration due to gravity. As a matter of fact, the only way that the forces could be the same on these objects and have the same accelerations is if they had the same mass. Projectile motion combines the constant horizontal motion of an object with the constant accelerated vertical motion. The constant accelerated vertical motion arises from the constant force of gravity acting on the projectile. There is no net force in the horizontal, thus no acceleration in the horizontal, and therefore the object moves with a constant horizontal velocity. However, in the vertical motion, there is a net force, and the object over here, dropped by this guy, would continue to go faster and faster and faster and faster. We treat each of these motions independent of each other. That is, motion in the horizontal and motion in the vertical, we treat independently of each other. Horizontal motion, we deal with constant velocity motion equations, and to deal with the vertical motion, we look at constant acceleration motion equations. There is one unit that crosses over between the two, and that would be time. And hopefully this makes conceptual sense. If the object falls for 3 seconds in the horizontal plane, I'm hoping that it makes sense that it will also have to fall for 3 seconds in the vertical plane. We do model the vertical motion using the quadratic formula. This can allow us to find quantities like the time in the air, the vertical position, or the vertical velocity of the projectile at any point in time. So keep in mind that any object that is just under the influence of gravity and close to the surface of the Earth, we can usually model using this mathematical technique. So here we have a cannon that's firing a cannonball out horizontally. As you can see, the velocity in the x direction initially is the velocity in the x direction is 20 meters per second horizontally. There is no vertical motion to start off with, so your initial velocity in the vertical would be 0. If we look 1 second later, notice that the velocity in the x direction, the horizontal motion, is still 20 meters per second. And that continues throughout the entire motion of the object. So even just as it's about to strike the ground, it is still moving horizontally at 20 meters per second. In the vertical motion, however, or the vertical velocity of the object, we start off not falling at all, and then 1 second later, we're moving at negative 9.8 meters per second squared, or pardon me, 9.8 meters per second. A second after that, we're going negative 19.6 meters per second. And a second after that, we're going 9.8 meters per second faster than the previous second, and that motion continues all the way down. So I'm hoping it's pretty clear at the moment that horizontally the object is not slowing down, but vertically the object is always speeding up towards the ground. And that's because the force of gravity is always acting downward, and it is constant. Remember, constant forces provide or produce constant accelerations. And it doesn't matter if we have the object being projected upward to begin with instead of horizontally. Here, this guy is throwing an object upward initially and also to the right. So in this particular problem, the vertical motion initially is positive. But because the gravitational force is acting downward, it's going to tend to slow the object down. So 1 second later, vertically speaking, the object is now going 9.8 meters per second slower than in this one. So now we're down to 9.8 meters per second. Horizontally, however, it's still traveling at 12 meters per second. Then we get to the peak. Well, the ball is going to eventually turn around, and it has to stop rising and has to start falling. So vertically, there is no velocity here. The motion is completely horizontal, or 12 meters per second. And then we begin to fall. 1 second later, 9.8 meters per second. 2 seconds after he reaches its peak, I should have said that. It's going, after 1 second after it reaches its peak, it's negative 9.8 meters per second downward. 2 seconds afterwards, negative 19.6 meters per second. But as it's falling downward, the horizontal motion remains the same. Quite often questions are asked about what goes on at the peak of the projectile's path. What's the object's velocity? What's the acceleration? And what is the time to get to the peak? Is the object accelerating at the peak? Absolutely. It's accelerating at 9.8 meters per second downward. Keep in mind, gravity is still acting on the object, even though it's at the peak. At the peak, we can also say that the motion is completely horizontal. It's not traveling vertically upward, but it hasn't started falling back downward either. So that initial horizontal motion is still present. How we find the time to get to the peak is a relatively simple mathematical step, but I'll go over that in a later video. Some of the power and the beauty of physics is that whatever the motion of the object is, whether we throw it upward initially, whether we throw it off horizontally, I guess we could also throw it downward as well, we don't need different sets of equations in order to describe those types of motions. The sets of equations that will describe this motion, a horizontally projected object, are the same as if we throw it upward. And that is rather amazing, or at least I find that to be rather amazing, that we don't need a different set of laws. Anyway, I hope that you have found this overview to be somewhat insightful and giving you some background into this. And I look forward to making more videos for you. Thanks for listening.